Welcome back to our discussion on the different metrics of photovoltaic energy conversion. The first metrics we discussed are all related to how much bang you can get for your buck. So how much solar energy can be converted under real world conditions and at what price. Another important metric in this respect is the reliability of a certain PV module. Crystalline silicon solar cells are very stable and reliable. Good quality crystalline silicon PV modules have guaranteed lifetimes of up to 35 years. This means that the energy yield over their respective lifetimes is relatively high, which in turn improves their cost effectiveness. There are other metrics, however, that are unrelated to the cost or energy yield of PV. One of these, essential for the upscaling of PV, is the abundance of material resources. The metric of material abundance can actually be split up into three separate metrics. These are 1. The abundance of the individual elements used for PV technology, and 2. The resource used per PV module. These metrics will be addressed in more detail in the next two courses of this program. Thirdly, there is the security or reliability of the supply chain for the required elements, which has been of increasing concern recently due to the global incidents of the last years. Let's take a look at the abundance of the elements. In this graph, the y-axis or vertical axis shows the number of atoms per million silicon atoms in the Earth's crust. The x-axis or horizontal axis shows the atomic number. We now populate it with the different elements found in the Earth's crust. We can indicate the rock-forming elements, which are most abundant and can most easily be mined. With increasing atomic number, the elements become less abundant. The rarest metals are indicated by the yellow area. The major industrial metals are indicated in red. These elements have a global production of at least 30 million kilograms per year. The precious metals are shown in purple. These elements are rare and very expensive. Finally, there are the rare earth elements. These elements are much more abundant than the precious metals, but do not have the tendency to become concentrated in exploitable ore deposits. Therefore, most of the world's supply of rare earth elements comes from only a handful of sources, which poses a risk to regional supply chain security. The elements used for crystalline silicon solar cells, such as silicon, phosphorus, oxygen and boron, are very abundant. This is one of the reasons why silicon PV has evolved to be the market leader it is today. Only silver, used for the metal contacts on a solar cell, is a precious metal, which could prove a challenge for the required terawatt scale implementation of photovoltaics. Research efforts are therefore devoted to the reduction of silver use per PV module. In the second course of this program, we will discuss that the number of elements used for some of the other PV technologies are much more precious and rare. The material abundance is not the only PV metric that can affect the large-scale implementation of PV. Another are the aesthetics. Aesthetically pleasing PV modules, such as these zigzag building facades, these PV modules with optical filters, or these semi-transparent thin-film organic solar cells, provide attractive options for architects and building developers that can help facilitate the implementation of PV on surface areas where PV would otherwise potentially not be considered. Similarly, the wider implementation of PV can also be facilitated through the development of thin, flexible and lightweight PV modules. Examples are this thin cell from Alta Devices and the flexible thin film silicon power foil from Hyatt Solar. These lightweight products can be installed on surfaces and roofs that do not have the load-bearing capacity to facilitate the implementation of conventional PV modules. This is the case for many older buildings and large industrial buildings. The flexible nature of these products can also help with other metrics for PV, such as the ability to fully cover complex surfaces and additionally provide ease of installation. Full surface coverage is demonstrated here in these thin film PV modules integrated in roof tiles and on corrugated roofs. These products, as well as this prefab facade with integrated insulation and PV module, additionally provide ease of installations since multiple build components are integrated into one product. Another important metric for PV, one that is quickly receiving more attention is the recyclability of PV modules. The first generation of commercial PV modules are starting to reach their end of life. The number of end-of-life PV modules will increase significantly in the next couple of decades, considering the 20 to 35-year lifetime of PV systems and the massive amounts of PV modules installed in the last decade. Currently, few countries have established schemes for the collection and recycling of these PV modules. In the few recycling plants currently in existence, only the aluminium frame and junction box, indicated in the visual, are effectively recovered. The remainder, including the glass plates, silicon solar cells and silver contacts, are crushed and used as building material, predominantly for roads. Processes to improve the recyclability of a PV module are technically, but currently not economically, feasible. Techniques already exist to separate the solar cells and encapsulant from the glass plate, which would allow recycling of the glass plate. Additionally, through standard metallurgical processes, the silicon and silver can be extracted from the remaining encapsulant solar cell stack. In the third course of this program, we will discuss the recyclability of PV modules in more detail. This ends our second video on the different metrics of PV energy conversion. We will continue our discussion of the metrics in the next video.